Yeah, in class, really no, that's me.
Okay.
Yeah, I'm just using my iPad.
Okay. Okay, can we get started? So this is tutorial 2. Any questions on the first one? It's the question 1, part 1. Can you all hear me on the internet? Joria, can you hear me?
Yes, Prof.
Okay, good. Any questions on the first one? Question 1, part 1. Anyone want me to go over question 1, part 1? Okay, this one, right? We're on tutorial 2. Question 1, part 1. The curl of a gradient function equal to 0. Any questions on that? No? No question, huh? So how about question 1, part 2? We want to show that the divergence of the curl of a field vector is 0. Any questions on that? Question 1, part 2? No? Okay, that. Yeah. Yeah. Can you repeat your question again? Yeah. I'm not exactly sure what you mean by that, but maybe let's discuss that. So you're talking about part 2, is it? Okay. Question 2. Oh, it's question 1, part 2. Sorry, it's the wrong one. I bring up. Okay. So you are asking this, right? So this is this del function is a vector. A is another vector. So the result of this cross product is a vector, right? And your question is this equal to 0? Is that what you're saying? 0 is a scalar or a vector. Up to you. 0 is 0. All the unit vectors are set to 0. No, but I mean, in this case, it cannot be 0. It's not zero. You have to assume your A vector to be something like here. The A vector is some AX coefficient with unit vector AX, some AY coefficient with unit vector AY, some AZ component coefficient with AZ unit vector. So you have to show it for this general case. You cannot say I'm going to let A vector equal to 0. Then of course everything is 0. Huh? Any questions on this, anyone? Is everyone okay this? So we move on to question 2. So if you have question, please ask. Otherwise, I'll continue to move on. Do you have any questions? Which one? Question 1, part 1? Okay. So where do you start? Question 1, part 1. So you want to show curl of the gradient function, right? So obviously you have to, curl means, of this gradient function means your del vector cross with that gradient function vector, okay? So that's what it means. So in my case, I prefer to write it with an arrow on top. Yeah, we want to show this, yeah, the left-hand side here. So I want to illustrate that this is vector cross product. So just prompt yourself there's a vector on top here. And this gradient f itself is a vector. Huh? Gradient f is a vector. So can you tell me what's this del vector? What's the del vector? Oh, quiet. What's the del vector? What's the del vector? Partial derivative. So what's the answer for del vector? That's not a vector, huh? You're missing something. D over dx ax unit vector plus d over dy ay unit vector plus d over dz az unit vector. Huh? Is that d or is that del? What's the difference? Yeah, what does partial differentiation mean? When you're differentiating with respect to x, for example, you keep all the other variables as a constant, right? That's what you need to do. Okay, so now, of course, what we have just said there is for Cartesian coordinates. Huh? If you are using cylindrical coordinates, the del vector is different, right? Anyone know what's the del vector for a cylindrical coordinate?
Del over del
That's phi, yeah.
Yeah, in the
Phi first or AR first? You know, radial first or phi first?
I don't know, one of them put R. Wait, which one is phi?
Okay, big question is, do you need to memorize all this? Let me show you the exam appendix, okay? It's in the exam appendix. Yeah, this is Cartesian. Hey, yeah. It's not directly there. It's implied there. It's implied there. Wait, implied in which equation? I want to see how which one of you get it. Implied in which equation for del vector? I think you know. Yes, exactly. It is in this determinant, right? This first vector is basically the middle one, right? Yeah. And of course, the unit vector is on the top now. So this del is del x ax, del y ay, del z az. Okay, this is for Cartesian. This is for cylindrical. Okay, now you tell me what's the del vector for cylindrical. No. Can you see already? Can you please read it out to everyone?
Oh, me. There are AR.
Yeah,
There
phi. Let's go phi. Del phi.
phi plus del Z A Z.
I want to hear your middle one again. What's the middle one?
Del phi A phi
You're missing an R.
R O.
You're missing an R, huh? And then, yeah, of course, overall, there's also one over R outside. Oh, okay. No. That one is probably more from the, no, not the del from the del. Okay. Yeah. There's the R.
So is it R or 1 by R?
There's the R there. Yeah. Where does that one over R come from? Huh? Where does the one over R come from? Okay, anyway, if you want to know where it come from, afterward, when we go to the lecture notes, we look at the lecture notes, you know. In fact, it's this week lecture notes in under cylindrical coordinates. Okay, so we are dealing with Cartesian at the moment. So your del is del x ax plus del y ay plus del z az. Eh? So that's your del function, del vector. What's gradient f? What's the gradient f vector? What's gradient f vector? Can someone please say it out loud? I mean, yeah, if you, please say it out loud. What is your gradient f function vector? Gradient f vector. Would you like to say it out loud? Everybody is quiet, so I don't know whether you know or you don't know. What is called a gradient function? How do you get a gradient of something? Yeah, differentiate that function with respect to each of the variable, assign it the unit vector in that vector, that variable, right? So in this case, when I say variable, it means the three axes, right? X, Y, and Z axis. So gradient f is del f by del x ax plus del f by del y ay plus del f by del z az, right? Okay, so it looks like actually, I don't know how, you know, it seems everybody is quiet because you have not tried. Oh, how many have actually tried this tutorial? Hands up, please. 1, 2, 3. Only 3% tried. Okay, anyway, so we want to do this cross this, right? This cross this. So therefore, the cross product is given by this determinant. So the first row you write is basically the unit vectors, ay, ax, ay, az of each of these vectors. The middle one is your del. The last one is this one, right? Your gradient f. Okay, so next we're going to expand out, right, from this determinant. So first of all, the ax unit vector, then we have basically is a plus, right? Remember, this is a plus, this is a minus, this is a plus, right? So we have del y of del f by del z. So we read this as del square, right? One d here, another d here, become del square f over del y del z, right? Del y del z. And then minus this times this, right? So del square f over del z del y. Are these two terms the same? Are these two terms the same? Well, you see the denominator is, you differentiate with respect to z first and then with respect to y. This one says differentiate the function with respect to y first and then with respect to z. Are they the same? So imagine, f is the here, describes the here. This is my x-axis, this is my y-axis, this is my z-axis. So I differentiate means I move in y direction first, and then move in z direction, let's say, right? Y and then z. Oh, I reach this point on the here. Or I start here, move z first, and then y. I still reach the same point, right? Except if that function is not continuous. If the function is continuous, if the here is continuous, it's okay. But if the here has a cliff on some point in y, let's say, right? Then if you move in y first, you fall down the cliff. Then cannot. Yeah. So condition is f must be continuous. If f is continuous, these two are the same, they subtract to 0. So no ax component. Okay, next one we go ay component. So this one is minus, plus minus, right? So that's why I have minus ay. So same thing again, you do a crossing like that, right? So you have del x of del f by del z, which means del square f del x del z minus del square f del z del x, right? So again, the order is reversed. So same, as long as the function is continuous, they are the same. So this also subtract to 0. So no ay component. And then finally plus az, right? The last one here, plus az. So del square f by del x del y minus del square f by del y del x, right? So again, if the function is continuous, they subtract to 0. So that's how we get 0, right? So in conclusion, this is read as the curl of a gradient function is always 0. This cross using this del operator is known as the curl of this function. Curl of this, whatever this field vector. This field vector is 0. That means gradient f don't curl, doesn't have any curling component. You want to cover part 2 also? Okay, so let's go on part 2. So part 2, we want to show that the divergence of the curl of A is 0. So let's do the curl of A first. We do this first. Curl of A. So curl of A means the gradient vector cross with the A vector. Right? So in this case, the difference is with number part 1 is A is your gradient f, if you like, but A is not a gradient function. A is some arbitrary field vector. So therefore, we let A to be some arbitrary vector first in Cartesian format. So that's why we say is some generic coefficient AX times unit vector AX plus some coefficient AY times unit vector AY plus some coefficient AZ times AZ unit vector. This AX, AY, AZ is in general a function of XYZ. Okay, so with that, we can now, obviously you have to form this first, right? You have to form the vector cross first, then the answer you do this dot, right? Agreed? Okay, so let's do the cross first, right? So what's the answer for this? So you can imagine you will have this, right? You have this, right? So, but in here is A, right? Your gradient f is your A vector, right? So the first row is still the same, the unit vectors of each of these vectors. Second row is the same because it comes from this del vector. The last row here is basically AX, AY, AZ, right? Those are the 3 coefficients we assume for the A vector, right? AX, AY, AZ. So therefore, the AX component of this cross product, right? The curl of A, the AX component would be del Y of A Z, right? Minus del Z of AY, right? Okay with that? Okay, then next component will be minus ay, right? And then we have del x of az minus del z of ax, right? And then finally, plus az, this last row. So del x of ay minus del y of ax, right? So that's what we have here. Okay, so next we expand out to do the dot, this del dot, the whole thing. So remember del is this, del is this, so keep this in your head, right? This is your del, right? So it has ax, ay, az, whose coefficient is basically the partial derivative with respect to that axis variable, right? Okay, so just remember that in your head. So when we deal with the ax part of this, we're del x ax unit vector, right? So when we expand out here, we're dot with this ax unit vector. Ax dot ax, what's the answer? What's ax dot ax? 1. Okay, so therefore we would have to continue with the coefficient of that. So the coefficient of that is del x, right? So what's del x of del az by del y? So you expand, becomes del square az del x del y, right? And then we go in the next term, become this minus del y ay, right? Del ay, so del square ay del x del z, right? With a minus. Agree with that? Okay, next that ax dot ay, what's the answer? Ax dot ay, what's the answer? Wait. Ax dot ay 0. Yeah, so no need to proceed anymore. Ax, finally ax dot az also 0, right? No need to proceed anymore. Okay, so then we go to the next unit vector of that one, right? Del y ay, right? So you have ay dot ax is 0. Ay dot ay is 1, right? So you have this minus that comes in here, that minus. So you have del y. So del square az over del y del x, right? Yeah, this term, right? And then expand in this one, minus become a plus. And then we have del square ax over del y del z, right? This term, right? And then again, expand with this is 0. So finally come to the last term of this, which is del z of az, right? So this 0 last here, right? Del az dot az is 1. So del z of this is del square ay del z over del z del x. Then this one is del square ax over del z del y. Okay, so now you inspect all these 6 terms, which cancel with which? If a is continuous, if a is continuous, del az, del square az, these two are the same, right? So this is a plus, this is a minus, they cancel each other, right? This one ay is down here also, right? So one is minus, the other is plus. Again, they cancel, right? Likewise, this also, right? With this, so they all subtract to 0. Okay, so we've shown that in conclusion, the divergence of the curl of a vector field is 0. Move on to question 2. Okay, question 2. Verify the divergence theorem. So first, state the divergence theorem. What's divergence theorem? What is the divergence theorem? Anyone can read it out in your own words? How do you read this? This del vector dot with A is known as, what is this known as? Yes, divergence of A. What does it mean, physically mean, divergence of A? Earlier on, we say curl of A, right? And I say curl of A means, does the A field vector has a arrow, going round and round, right? That's curling, right? That's where the word curl comes from. Divergence of a field vector, what does that mean? It's whether the arrow of the field is, has an angle of diverging, right? The angle is diverging. As opposed, they are not parallel. Yeah. If it's parallel, then divergence is 0. Can you visualize? If the A field has arrows that are parallel, then the divergence will be 0. Yeah. If the arrows, at first are closer together, then moving further and further apart, or the other way around, yeah, further apart and then moving closer and closer in, means it has finite divergence. Okay, so this is read as the divergence of A when integrated over a volume. Oh, that is a finite volume, integrated over a finite volume. That finite volume is bounded by this surface here, this so-called cross surface on the right-hand side. So the divergence theorem say that it's equal to that field vector A, the same field vector A, dot with each of the surface area enclosing that volume. That's what the divergence theorem say. Okay, so let's try and visualize, okay, this problem. So the problem here first start with A field given by this equation. So you can just draw a three-dimensional problem here, figure here, and visualize the A field as something in red. Draw any arrows you like. So that is your A field, vector field, in three-dimensional space that you visualize. If you want to be very accurate, or you're using a computer-aided design package to draw that field, what the computer-aided design program will do is basically subdivide each of the X into discrete steps. That means it's a grid. You form a grid, three-dimensional grid. And at the grid point, you substitute the X, Y, Z value and calculate the AX, AY component. And then from there, you draw an arrow direction according to the direction of the field. And the length of that is proportional to the magnitude at that point. So that's how you visualize. Okay, so next we say that this divergence theorem, what we do is we find the divergence of A over a finite volume. What is that finite volume in this problem number 2 is that it's bounded by this fixed surface area of a cube. So the cube is formed with X from 0 to 1, Y from 0 to 1, Z from 0 to 1. So there are 6 surfaces of this cube, right? The front surface, which are labeled number 1, back surface labeled number 2, right surface labeled number 3, left surface labeled number 4, bottom surface number 5, top surface number 6. Okay, so these 6 surfaces of the cube encloses the volume. Okay, so let's now show this divergence theorem is true by first evaluating the left-hand side and then evaluate the right-hand side and show that the two evaluated values are the same. Okay, so let me start from the left-hand side. So we need to form the divergence of A, right? Which basically take this del vector, dot with your A vector. What's your answer? Here's your A vector. So in your head, you remember your del vector is del x ax plus del y ay plus del z az, right? So let's start with the ax component of del. Start with ax, dot ax is 1, right? So I have xy, right? And then the coefficient of that del vector is del x, right? So what's the answer? Y, exactly, okay? So we have y. Then this one will be the next one, right? The del y of the del, right? Vector ay, right? When ay dot ay is 1, right? So del y of this, right? The answer is z, right? I'm happy to hear you say z. Are you Singaporean? You are. Someone told me in Singapore school you are taught Z, not Z. I'm taught the British way, so we call that Z, not Z. Z is I think the American way, right? Huh? Depends on the person. Yeah, you're right. Yeah, depends on your teacher. Yeah. Okay, final one. Okay, del z az of the del, right? Vector start with az. So del z of this is x, right? So we have this. Okay, so now we substitute this in here. You can see this is now a scalar quantity, right? Yeah, because the vector dot product of two vectors is a scalar. So this is scalar quantity. We need to integrate it over that volume that is bound by this surface, which of course is by x0 to 1, y0 to 1, z0 to 1, right? So we take the unit volume. The dv is basically dx, dy, dz, right? The little cube, increment in x, increment in y, increment in z, right? So that's your dv, dx, dy, dz. So you do dy, dz, dx, or dz, dx, dy, up to you. This is a cube, no difference. Okay, so the limits for x 0 to 1, y 0 to 1, z 0 to 1. Okay, so now let's do the first innermost first, right? So we are integrating y plus z plus x with respect to x. So 3 terms in there, integrate with respect to x. Let's do one term at a time. Integrate y with respect to x. What's the answer? xy, right? Y is just a constant, huh? When you're integrating with x. So therefore, xy or yx, up to you. So that. Integrate z with x. Yeah, exact, right? Integrate x with x. Yep, x squared over 2. Thank you, thank you. Yeah, someone respond. I'm happy to hear that. Okay, so we put the limits of x 0 to 1. So when you put the limits x 0 to 1, so 1 first and then minus the 0, right? 1 here means this will be y plus z plus half, right? And then minus 0, 0, 0, right? Okay, so therefore we have next, remember this is y, this is z, this is half. Huh? We now next integrate with y. So y integrate with y, answer is yeah, how come the rest so quiet? How about those on the far away? Can you say something? Integrate y with respect to y, the answer is thank you. Still her. I'm going to give her full mark. The rest of you all 0. Okay, and then next one, this one is z, right? Integrate z with respect to y. What's the answer? Integrate z with respect to y. Yeah, zy, right? Or yz, right? Okay, finally, this is half, right? Integrate half with y. y02, yeah. Okay, so then put 0 to 1. So we have half plus z plus half, right? And then we are integrating with z. So half, you get z over 2. Z, you get z squared over 2. This half again, so z over 2. Then you substitute z of 1, you get 3 over 2. Okay, that Okay, so that's our left hand side. Next, let's do the right hand side. Ah, this is tougher now. Right hand side. Can you see what does this expand to? What would this expand to? This right hand side. What does this right hand side expand to? Yes. So when you hear what he says, right? Depends on which plane you're looking at, which surface are you looking at? How many surfaces are there? 6. That means expand to 6 double integral. Huh? Expands into 6 double integral. Okay, let's do the first one first. First surface. This one, the front surface. What is the A value for the front surface? Is it just this? What's this A value for the front surface? Is it this? No. You take this and what do you do? What do you do? Exactly. You have to substitute x equal to 1, because this surface is located at x equal to 1, whereas this is a general expression for your A vector in 3-dimensional space. But you want to force it so that the A vector lie on this surface. So you must set x equal to 1. This is one common mistake. If you do that mistake, you will get the right hand side wrong for that surface. You all hear me correctly? Okay, now what's this ds for the first front surface? That surface number 1. What's ds? This way, right? This way is dy, up is, yeah. So dy dz is a vector. Where's the vector direction of that surface? Dy dz. Positive ax. So remember, the vector of a surface is always that normal to it, perpendicular to it. So now the question is that perpendicular to this surface? Obviously is perpendicular means perpendicular to this surface is this way, right? Or in, right? Out or in. So by definition is out of the volume it enclosed. Out of the volume it enclosed. So in this case, positive ax, positive ax for the first surface. Okay, now tell me the next one, the second surface, right? What is ds is the same, right? Agreed. And direction will be the back surface here. What's the direction of this back surface? Minus ax. Okay, and the A vector? Is set at x equal to 0. So only this term remains. Yeah. Okay, third surface, this right surface, what's the ds value? Yeah, dx dz. Direction? Yeah, positive y. Okay, and then the A vector for this surface? Exactly. Set y equal to 1 here, y equal to 1 here. And this one remain as xz, right? Okay, so then the fourth surface, ds. Fourth surface for this ds. The ds value, same, right? As the third one, right? Direction is, yeah, negative ay, right? And then again, the A vector is force with, yes, y equals 0. So this is 0, this is 0, only this time remain. Okay, finally, bottom surface, oh, not yet, finally. Bottom surface, what's the ds? Yeah, dx dy, direction? Yeah, negative az. Okay, and then the A vector is force with, yeah, z equal to 0. So you're left with this. Then finally, the top surface. same dx dy, right? Direction, positive az, and then a vector is force with z equal 1. Okay, okay, so that's what I have here. Okay, explain into 6 surfaces. Okay. Okay, so explain into 6 surface, so 6 double integral. I haven't substitute in the a, but I just leave it as a first. Yeah. So the y, we are going to do a dy dz, right? For the ds, for this the first surface. So y vary from 0 to 1, z vary from 0 to 1, right? This is the back surface, right? This is the left, right, this is left, bottom, top. So I just prompt myself that each of these surface, the setting that you're going to use into your A, which I'm going to do here. So I took 2 steps to finally do this. Do I need to go into all this detail, or is clear? Okay, so eventually when you integrate, you end up 3/2. Okay, with that. Any other questions that you may have on this question 2? Anyone has some questions on number 2? Anything that you want to clarify? Okay, let's move on to question 3. So question 3. You're given a field vector A. And in this case, the A vector is only 2 unit vectors, no AZ component. You're asked to find the closed contour integration of A dot dl. So what this means is that the A vector in this two-dimensional space of xy is somewhere here. You can visualize them in some arrows by red color. So when you take the dot product of that A along this DL, okay, so this I'll call it line number 1, and then go up this second line. This is line number 2, and then go down left this way, line number 3, down this way, line number 4, to eventually close the loop. Okay, so that's why this closed loop. Just like, you know, the divergence theorem is a cross surface, right? That encloses a volume, but this closed loop encloses an area, right? Yeah, you can see this closed loop encloses the area F. So if you take the curl of the A vector, of the A field, right? A vector field, if you take the curl of it, integrate it over this area that is bound by this closed loop, is your second part, your B part. So if you look at Stokes' theorem will say that these two are equal also, right? The A equal to B. That's it. Okay, so let's do A first. So it's the same thing, right? Your A value when you're going along here is force with what in this equation when you go along this line number 1? What's the fixed by what? Yes, fixed by y equal to 0. So your A equation, when you use it in here for this first line, your A equation, you have to set y equal to 0. So it's just 2x squared ax minus y squared ay, right? Okay, when it's along here, line number 1. So that's your A value. The DL value along this line is incrementing in x, right? In the direction of AX, right? So it's dx AX unit vector, right? And then you're integrating from a length of 0 to the length of 2, from a length of 0 to a length of 2. Okay, so that's our first line. Now we're going to do plus, so we're going to do the second line, right? Plus this. So again, our A is this equation, but forced with, yes, x equal to 2. So you put x equal to 2 in here. That's your A value along here. And then your DL is, you are incrementing in y, so dy, and the direction is positive AY. So you're integrating again from a length of 0 to 1. Okay, now the third line down this way. So our A vector now is force with, force with y equal to 1. And then we are also incrementing in x in the direction of negative AX. And then we're integrating from a length of 0 to 2, from 0 to 2. Not from 2 to 0, from 0 to 2. Always think in that way. Incrementing in length, not the direction. The direction is taken care of by the DL direction. Okay, so finally the last line here, same thing again. Our A will be forced by, fourth line, A will be forced by here. Yeah, put x equal to 0 in here. And then your DL is incrementing in dy, right? Direction is minus AY, right? You're integrating from 0 length to 1. Okay, so that's how we should be formulating that. And I'll show you the. Okay, so that's why we expanded into 4. 1, 2, 3, 4 terms. Okay, so and then these are the detailed evaluation. Do you want me to go over the detailed evaluation or is clear already? Anyone want me to go over the detailed evaluation? It's just a dot product, so it's quite straightforward, right? A dot this, right? So A is, of course, this equation, but forced with the condition along this line. Right? So AX dot AX, of course, is the one that will be 1. Right? AX dot AY will be 0. Right? So it's this with y equal to 0. So therefore, it's just 2x squared. Is it okay for me just to illustrate one? The rest you can work it out yourself. Yes, huh? Okay, so eventually when you do everything, you find that actually the numeric answer is 0 now. So happen because the one is plus, the other is minus, plus, minus, plus, minus, or minus plus. Okay, so for the B part, you want to form the curve of A, right? You want to form the curve of A. So A is given as this, this your A, right? And of course, this curve of A means your del vector cross with it, right? So this is your del vector in two-dimensional space, right? XY. So in this case, just expand when you do the vector cross, just expand it. So let me expand AX cross AX. What's the answer? AX cross AX. What's AX cross AX? AX dot AX is 1. AX cross AX is 0. AX cross AX is 0. Okay, next, AX cross AY. Yeah, we're now expanding this first with the second one, right? So AX cross AY. AZ, positive AZ, yeah? Positive AZ. Okay, so that's why I have AZ here. And then I have this del X of this 2xy, del x of 2xy. So 2y, right? And then del x of minus y squared, so 0, right? Okay, next I expand this ay component of my del, right? So ay cross ax, what's the answer? Ay cross ax minus az, huh? Minus az, huh? Ay cross ax is minus az. So I have minus az as my component. I have del y times del y of 2x squared is 0, right? And then del y of y squared is 2y, right? Okay, if I continue, finally, you know, ay cross ay. What's ay cross ay? 0, right? Okay, so therefore end up just this. And on and behold, one is positive, the other is negative. So answer is 0. So if the curl of a vector is 0, it is irrotational. Huh? Yeah, it's not curling, means it's irrotational. So I'm answering the part C from this answer now. And of course, there's no need to proceed and do this dot product over the surface area, right? Just 0 dot with something will still be 0 anyway. Yeah. So no point proceeding already. If you want to insist to proceed, how do you formulate ds? What's ds equal to? Can someone tell me what's ds equal to? What's ds? Look at this figure and tell me what's ds. So remember, this closed loop encloses the surface, which is this S, right? So what's the ds? Dx dy. Direction? Positive az. Huh? So you use your right hand and then use your fingers curl along the direction you're doing the cross contour. That cross contour. Cross loop integration. Oh, that's the direction of your thumb, is the direction of your surface. Okay, so if you need to continue to evaluate, I'm saying, yeah, we need to continue to evaluate this. Is got some question? The direction of the vector, this ds, because this ds is a vector. So what you have to do is you go and look back, because we, you know, this is Stokes theorem. So Stokes theorem is saying is that the A part, which says that this closed loop integral of A dot dl. So when we do this closed loop integral, we are going round like that, right? So we use the fingers to denote that going round. Then the direction of our thumb is the direction of the area. So if we integrate, I mean, if this is going this way, then you'll be negative. That's using Stokes theorem now. Of course, this question didn't ask you that A equal to B. Yeah. Okay, so I think we completed all 3 questions. And any other questions on tutorial 2? If not, remaining time, we are going to look at what you should cover in terms of your lecture videos, your lecture notes, your lecture slides. So as usual, I'm going to point you to what is the next tutorial questions like. So here's our tutorial 3. Next week tutorial. So question 1 asks you to find the electric potential, determine the electric potential V at some point Z. Or not at some point Z, as a function of Z, as a function of Z. Yeah, basically you want to find out how V varies with Z. And from that answer, you're going to find the electric field intensity along the z-axis. That's the reason why we want to find V as a function of Z. Yeah, because we want to find the E field along the z-axis. So what is the relationship between electric potential and electric field intensity? Anyone? Those who have read the notes, how do you get electric field intensity if you know the voltage? You probably know. What's the answer?
You take the gradient of it.
Thank you. Yes, negative gradient of V. Yeah, negative gradient of V. Yeah, remember gradient of a function in which in this case is voltage, right? The electric potential is a vector. Okay, so maybe we go and look at the notes, see which set of notes have all this. With 3 notes. Okay, so here you should see that there are 6 sets of slides, is it? No, 9 sets. Yeah, 9, 7-1, 7-2, 7-3, 8-1, 8-2, 8-3, 9-1, 9-9-3. I think you only need to cover up to 8-2, if I remember correct. Certainly down here is magnetic field already. I think starts from 8-3 is magnetic field, which is your following tutorial, I think. Tutorial. Yeah, applications of magnetic field start from 8-3. So if you don't have enough time, you just need to cover the first five. Okay, let's look at the first one. First one, talk about electric flux density and Gauss law. Electric flux density is given by this symbol D, right? D. Why do you need to introduce electric flux density? You can see they are actually related. Electric flux density and electric field intensity, right? They are related. D is equal to epsilon E. So why introduce electric flux density? What do you think? By multiplying it with epsilon, you find that actually D is independent of the medium, right? D is independent of the medium. D just depend on the charge, amount of charge, and the geometry. Whereas E would depend on the medium. Yeah. Okay, so in general, the epsilon will expand to epsilon naught times epsilon r, right? And epsilon naught is, of course, the free space permittivity. Epsilon r is depending on the medium material. So you can see some typical values of epsilon r. And you notice water is very high compared to the others. So remember, if you make this higher, then your electric field intensity will become lower, right? Yeah. It's 1 over it, right? D won't change, right? Electric field intensity will change. It will become lower for the same amount of charge and geometry. So in short, you can hold more charges if you use a high epsilon r. So that's the reason why if we want to make a big capacitor, large value capacitor, do you all realize that big capacitor are all electrolytic capacitor? Why is it electrolytic capacitor? It's because there's a liquid in between the 2 electrodes, right? Yeah, so it's filled with liquid. They don't fill with water. Water conductivity is still relatively high. So they have to find a liquid that has has a better conductivity than or lower conductivity, more of a dielectric than compared to water, but still with high permittivity. Yeah, that would be the ideal liquid to use. Okay, Gauss law. Where's Gauss law? This is Gauss law. Does this look familiar to you? Divergence theorem, right? This is the right-hand side of divergence theorem. This is looking like the left-hand side of divergence theorem. What is in place of rho v in the divergence theorem? D is the field vector, right? Divergence of D, right? Integrated over the volume is equal to this, right? Agree? So that's why you find that divergence of D is actually rho v, volume charge density. Divergence of D is volume charge density. So where do you use this? I mean, okay, one kind of use is you could calculate what is D knowing rho v. Okay, let's move on to the next set of lecture notes. If you have questions regarding any of these lecture notes slides, just please ask. Okay, next is introduction to electric potential. So here is where we then have what is electric potential relationship with E, right? So E is minus gradient V. So just prompt yourself, gradient V has an arrow on top, and so yeah, it's a vector. And the physical meaning is basically work done per unit charge. So the potential at this point, electric potential at this point, is equal to the work done by moving a unit charge from where to here? Infinity to here. From infinity to here. Potential is always a relative potential. Yeah. So if we talk about potential at a point, that relative is from infinity. Yeah. So this one is, of course, you are. So in this case, we are talking about the potential difference between 2 points. So the potential difference between 2 points is the work done to move against the electric field in the distance that you travel. So that's why it's E dot dl from that point number 1 to point number 2. And the negative sign is there so that if you are moving against the field, you are actually aiding in work. Whereas if you are moving along the direction of the field, then no, it's actually just the field that's pushing it, doing the work. So you're losing energy, right? Okay with this one? Any questions on this, all these slides? Third set. Let's move on to the third set. Nature of electric field and electric potential due to charge distribution. So again, when we first started with electric field, we talked about electric field due to a point charge, right? Then we move on to a line charge with some uniform charge density rho L. Then we talk about even moving in another dimension, so surface charge with uniform charge density rho S, right? And then finally volume charge in three-dimensional space. So same thing here, electric field start from point charge, line charge, surface charge, volume charge. I would strongly recommend you just start from point charge. Derive all the rest from there. That's how you solve real life problem anyway, because you may be given a problem that is not uniform charge distribution in a line charge, for example. So you start from a point charge, it's okay. You formulate it in such a way that your summation due to all the distribution of charge along the line, even if they're not uniform, you can do an integration to take care of it. So likewise, from there you can expand to surface or volume. So always start from the point charge equation. However, just take note that your exam appendix is always given as the volume one. Yeah. Here's the electric, here's the voltage. Just treat this triple integration rho v dv is basically a total charge. Yeah, just like remember your electric field here also, right? This triple integral rho v dv is your total charge Q for point charge. And remember that R vector is the vector pointing from that point charge source to where you are observing your E, right? That's where your R vector is. And this R in the denominator is the magnitude of that, right? So in your voltage equation, this R is basically the magnitude of that R vector, that same R vector that is pointing from your source, your point source, right? Your charge port source. Your charge is the source of your electric field, as well as the source of your voltage. So it's pointing from that to your where you're observing it, so where you are interested in your potential. That's your R. It's a scalar quantity. So hence V is a scalar. There's no direction. Okay, what else is in this set of slides? I think all these now are working out the details. I'm sure your tutorial, you'll start that way. Do it that way. Curl of E is 0. Electric field for static electric field is always irrotational. Static electric field. Okay, so that's the third set. The fourth set. Review of Ohm's law. What is Ohm's law? What is Ohm's law? V is equal to IR. Okay, let's start there. V is equal to IR. Okay, so we all should be strong in circuits. We know that circuits, when we construct a circuit, we have conductor to conduct the current I, right? Yeah, so here's the illustration. Let's just talk about that wire, okay? So here's a wire in blue. It has a diameter S. It has a diameter, let's say, or 1 millimeter. So pi or radius of 1 millimeter. So pi r square is the surface area of that wire, right? And then we have some length of the wire, right? So when we talk about current flow, that you measure in your ammeter, is actually flow of all the charges in that surface area S, right? Crossing that surface area S, is the rate of change of that charge, right? The flow rate of that charge, right? Time. That is your current, right? So is the charges distributed uniformly in across that cross-sectional area S or not? Okay, that will depend on the material, right? If this is a homogeneous material, you agree with me that it will be uniform, right? Yeah. So in short, to account for non-uniform medium, let's say, in a real medium here, then the amount of charges flowing in this part and this part may be different, right? So in this case, it's more meaningful to introduce another term known as current density, J. So the actual current is current density times surface area. It's a dot there, dot product. J is a vector, S is a vector. So J dot S is the current flow. Yeah, so in terms of the is more meaningful to look at it from that viewpoint of current density J. So let me ask you, just now I say, no, I have this 1 millimeter radius wire. Let's say it's homogeneous copper wire. So earlier on we say A, the current flow, or the charge distribution, right? That means the current density is uniform, right? Across that cross-sectional area. That is true if it's static. No, not meaningful to talk about static, right? That is true if the flow, the charges are moving at constant velocity. If the charges are moving at constant velocity, basically we have a DC current. Agree? Now, let's think about what if the charges are moving with varying velocity? Give me an example of varying velocity. What kind of current would you get? Sinusoidal. Yeah, so it's changing in velocity with time, but periodic. So AC signal, sinusoidal signal, yeah, AC signal is that kind of example. So whenever you deal with AC signal, you think of that repetitive frequency, right? So if I start off with an AC current of 1 Hertz, and I keep increasing it. Let's imagine you're using this in your 5G handphone. You know what's the carrier frequency of your 5G handphone? Around 5 gigahertz. So do you think the current distribution is still uniform at that frequency? It's no longer uniform, huh? That's why we have the expression skin depth coming in. How many of you here heard of skin depth? Skin depth. Any of you heard of this expression, skin depth? If you haven't heard of it now, never mind. Later on, you will learn it. So what happens is, as you increases that frequency of your AC signal, actually the current is confined around the surface only. It doesn't go inside, it's all flowing on the outside of the surface. Yeah, it's all on the outside of the surface. You cut a hole in the middle, no difference to the resistance, still the same. What is more important is the smoothness of the outer diameter. So in fact, high frequency, what do? We use gold plating to make it really smooth, because the skin depth, where most of the current density is concentrated, that's what is called skin depth, okay? It's the depth that the current density is concentrated. So when you're talking about 5 gigahertz, you're only talking about microns, tens of microns. That's how much metal you need on it. The rest is no use. You might as well drill a hole through it. Okay, so if you continue and derive, you'll find this magic formula here, which says current density equal conductivity times electric field. Okay, so current density is equal to the conductivity of the material times the electric field. So the direction of the current density is equal to the direction of the electric field. Okay, and then if you another very important thing is, earlier on we saw that divergence of D, D is your electric flux density, right? Is equal to volume charge density, right? Rho V. So if you expand D by epsilon E, you will end up, and then replace E by negative gradient V, you end up like that, right? Which you expand out, you see is actually del square V. is equal to minus rho v divided by epsilon. This is known as Poisson's equation. So one use of Poisson's equation is you integrate these 2 times, you get the voltage. If you know the volume charge density. This one you've seen already, curl E equal to 0 for static electric field. And this one is divergence of E indirectly, right? This divergence of D is indirectly divergence of E. Is related to volume charge density. Okay, so that del square is actually del dot del, right? So it's a scalar quantity. Yeah? The del vector dot del vector is also known as the Laplace operator. And Laplace equation is a special case that when your rho v is 0, when there's no volume charge density, then the del square v is also 0. Okay, that's the second. Okay, so one last one. Cylindrical coordinates. Okay, so early on we started with says y, right? Why is it in the exam appendix? There's the 1 over r, right? Go ahead and revise this. I think you will talk about all this in detail. How to map between Cartesian and cylindrical. Yeah. So go through this set of slides. It's important to understand how to then manipulate in cylindrical, which you will need to use from now on. Yeah, the moment you go into magnetic field, because magnetic field, you think about the field going round and round, right? So when they're round and round, spherical is more natural, or spherical is the most natural. But if it's only round in one axis, then going up, then that's cylindrical. Spherical is not in our syllabus. We just cover cylindrical only. So please go through this set of slides. Important, to know the basic of it, rather than just use formula. If you blindly use formula, you may go wrong. Okay, stop here. Any questions, anyone? Those of you who have not signed the attendance, please come and sign it. Daniel, you are here. Song Chen.
For last week I came, I forgot to sign my attendance.
It's okay. Last week we only start from this week. Yeah. Yeah.